So in the last session, we talked about the expansion of the universe and more specifically how the matter and energy content of the universe affects the dynamics of how the universe is expanding. How is that expansion rate changing with time? We talked about how if we have a universe that contains lots of matter, we're going to have a closed universe where that expansion rate will slow down and the expansion will eventually turn back around and cause the universe to collapse on itself. This one was if we have a very high amount of matter. We also talked about if we have a low amount of matter, then the expansion of the universe will just continue forever. And if we have this kind of critical universe, just the right amount of matter density, the expansion rate will slow, but never quite stop and turn around. We also talked about how the dominant mass in the universe seems to be this dark matter, this material that seems to be gravitationally affecting the objects around it, but we can't actually directly detect its mass. And that means that the overall amount of mass will have an effect on which of these universes actually describes our own. It changes how we view the past history of the universe and what the future of the universe is going to look like. One other thing that is related to this, in a previous session, we talked about how the inverse of the Hubble constant, if I do 1 divided by the Hubble constant, we get a time scale for approximately how old the universe is, which was pretty close to the currently accepted age of the universe. But I mentioned how the more detailed calculation depends on what sort of material is the universe made out of? What is the composition of the universe? And that's what we're kind of expanding on a little bit more here. If we have a universe with a lot of mass, then its prior expansion history is different than if we had, say, an empty universe or something that has very little mass and energy in it. We compared this to an analogy of me throwing this object up in the air, where its motion up and down is trying to be an analogy for the expansion of the universe. If gravity is too strong for a given, launch speed, then when I throw this up in the air, that expansion, the motion of the object through the air, it's going to slow down, eventually stop, turn around, and collapse in on itself. But we could imagine that if I'm on let's say a small asteroid with very, very low gravity, and I threw this object up in the air, it might never actually come down if the gravity is not strong enough. So we talked a little bit about identifying the mass content of the universe, and based on the amount of matter and dark matter, that's constitutes about 30% of this critical density. So for the composition of the universe, we've got about 30% matter, 30% mass, which is around 5% ordinary matter, and 25% dark matter. These are approximate. We'll talk about more specific ones a little bit later. But this suggests that we're going to have a universe that's going to expand forever. This case where the expansion rate slows down a little bit, but we still get that nice expansion forever. But we always want to try to say, are there other ways that other lines of evidence that we could use, other kinds of observations that we could use, or experiments that we could do to better understand these systems and to check that our understanding is actually accurate? How do we try to test our scientific hypotheses and our scientific theories? So astronomers want to try to find ways of independently measuring how has the expansion of the universe changed over time. And the idea for this is we can look at more and more distant objects. The further away those objects are, the further back in time I am looking. So eventually, if we start looking at objects that are far and far enough away, then the past history of the expansion of the universe is going to affect the redshifts that we see, the distances that we see, some other kinds of measurements that we can make. As we look further and further away, we will see those objects as they were further and further into the past history of the universe. So if the expansion rate has changed, we might be able to detect a signal in there. And this is what astronomers did with white dwarf supernovas. So let's mention these real briefly. So those white dwarf supernovas are standard candles that we can see from very, very great distances. When we talked about the different kinds of dead stars, we said white dwarfs might start pulling in material from a nearby neighbor, adding to their mass little bit by little bit. But if their mass passes that Chandrasekhar limit, that 1.4 solar mass limit, then that entire white dwarf star is going to go through a white dwarf supernova, completely obliterating itself. But we can see these titanic explosions from very, very far away. So we use white dwarf supernovas to see very, very far away events. Very far away or far back in time. So using these white dwarf supernovas, scientists were trying to identify how has the expansion rate of the universe changed over time. And what they found was utterly unexpected. What they found is that instead of the universe as it expands, instead of that acceleration, instead of the expansion of the universe getting slower and slower, so the universe is expanding, but as it expands, it's slowing down. What they found is that the rate of the expansion of the universe has been accelerating. So by using these white dwarf supernovas, we identified that the universe is accelerating. Universe expansion is accelerating. I really can't overstate how unexpected this was. Scientists were intending to find out, well, how rapidly is the expansion of the universe been slowing down? If there's a lot of matter, if there's a lot of matter in the universe, it should slow down rather quickly. If there's less, it'll slow down at not as great a rate. But no one was expecting the universe to actually, the expansion rate of the universe to actually be increasing. Going back to the analogy of me throwing the object in the air, you can imagine trying to do an experiment and saying, well, how, let's say I'm on some unknown planet or some unknown asteroid, and I'm trying to figure out how much gravity there is there. I can imagine trying to do an experiment and say, I'm going to throw this up in the air and watch that motion to see how much gravity there is. Imagine trying to do that experiment, and when you throw the object up in the air, instead of like slowing down and coming back to you, instead of doing any of that, it starts moving upwards faster and faster and just launches itself into space. That level of surprise that you would probably have, that's what these astronomers were basically facing when they saw, oh, the universe isn't actually, the expansion rate of the universe isn't slowing down, it's actually speeding up. So again, this was utterly unexpected, and it's when we make utterly unexpected observations, those are the most exciting times for scientists. So none of the ordinary matter that we've talked about, things made of protons, neutrons, and electrons, so ordinary atoms, photons wouldn't do this, neutrinos wouldn't do this, the proposed dark matter particles wouldn't do this. none of what we've talked about would cause the universe to accelerate in this way. So we give a special name to whatever happens to be driving the acceleration of the universe, and we call this dark energy. So whatever is driving the expansion of the universe, whatever is driving the acceleration of expansion, we call dark energy. So a couple of important points about this. In a similar way that we said dark matter is a placeholder name for whatever is causing these effects of galaxies to be rotating too quickly, clusters of galaxies to be moving too fast, too much gravitational lensing. Whatever is causing that effect, we give it the temporary name dark matter because it's just a placeholder for whatever that actually happens to be. A similar kind of thing for this dark energy. We do not know the physics that is causing the universe to be accelerating, but we can measure this effect. So whatever is causing this, we're just calling that dark energy. One thing that could potentially cause it is, let's say that space itself has some kind of energy associated with it. Then if space were to expand, as we get more and more space, that would actually increase the amount of energy associated with that space. And this could have the effect of driving the accelerated expansion of the universe. Is this what's actually causing the acceleration of the universe? We don't know. We haven't determined what this dark energy is, but again, we see its effect on the acceleration of the large-scale geometry of the universe. We don't know what this energy is. So we don't know what it is. But the energy density associated with this dark energy seems to stay constant even as the universe is expanding. When we talked about matter and radiation, as the universe expands, stuff moves further apart, so that energy density decreases. It doesn't seem to do that for this dark energy. So we don't know what it is. It seems to have a constant energy density. Even as the universe expands. When we talked about the Big Bang Theory, and I mentioned that Einstein's equations predict that the universe should either be expanding or contracting, but Einstein didn't like that idea at first, so he tried to put in this kind of correction factor to balance out the universe. And he said it was his greatest blunder in life, not being able to use his own equations to predict the expansion of the universe. It turns out that Einstein might be vindicated because the mechanism he proposed, something called the cosmological constant, something very similar to that could also cause this kind of accelerated expansion. Again, is that the answer to what this dark energy is? We currently don't know. But in order to identify some of the properties of this dark energy, or to know that this is an actual thing, we probably want a little bit more data. Well, when we look at the cosmic microwave background, when we look at that CMB, the cosmic microwave background suggests that it has the properties of a flat universe. So the CMB properties work for a flat universe. So a flat universe in that the total energy, mass and energy density should be at that critical value. But we said the ordinary matter and dark matter together only accounted for about 30% of that critical mass energy density. So if the ordinary matter and the dark matter account for about 30% of the critical mass density, then dark energy has to account for the rest of the 70% of the mass energy density of the universe. So to get this working, this implies 70% of the universe, or of the universe's energy, is dark energy. Again, whatever dark energy happens to be, it seems to be one of the main ingredients in the universe that we see around us today. And the cosmic microwave background, how much that temperature of the cosmic microwave background fluctuates across different regions of the sky, that seems to match that dark energy needs to make up about 70% of the universe. So when we go back to the composition of the universe, in fact, let me just copy this down to the bottom so we can kind of put everything in the same spot. We've got about 30% mass, so 5% ordinary matter, 25% dark matter, and around 70% of this should be dark energy. Again, whatever dark energy actually happens to be. So this graph is looking at how much mass density we have. So let me kind of highlight a couple parts on here. I think this might be the easiest way. So this is the mass density. And this part up here is dark energy density. And basically mapping out, well, what observations can we make to identify how much mass density there is and how much dark energy density there is. And we have some different methods of actually trying to make some of these observations. For example, the properties of the cosmic microwave background. As I said, it suggests that the universe overall should be around approximately flat. So this kind of diagonal band here are all the values of mass density and dark energy density that seem to be consistent with the cosmic microwave background. We talked about those supernova observations that suggested the expansion rate of the universe was increasing. The universe's expansion is accelerating. Well, those observations, according to them, the properties of the mass density and the dark energy density that match up with each other, that match up with those observations, should be somewhere in that region of the table. We've got other methods of measuring some of this. This is called baryonic acoustic oscillations. We're not going to worry about those properties, but we also said just in general that based on the amount of stars we see, based on the amount of dark matter that we happen to detect, the dark matter density should be around 0.3, should be around 30% of the critical mass density of the universe, which matches up with some of these other observations. And we notice that there's one part on this graph where all of those different observations, all of those give consistent data. If we had generated this kind of graph and there wasn't any one point on the graph where all of these observations aligned with each other. Like, let's say I made some other observation that said, oh, the mass density and the dark energy density, it should be somewhere over here. And then another observation saying, no, the mass density and the dark energy density should be somewhere over here. There would be no spot that's consistent with all of the data. That would demonstrate that there's something fundamentally wrong with the models that we're proposing. But introducing this dark energy density, it seems to match a number of different properties about our universe from a number of different sources. And again, the overall composition of our universe that we see, it's about 5% ordinary matter. Again, I was a little bit off in these numbers, so I'm not going to be super worried about getting the exact numbers for each one, but around 5% ordinary matter, around 27% dark matter, and around 68% dark energy. And again, that model seems to be consistent with a lot of different kinds of observations. Observations of supernova, measuring how much has the universe's expansion changed in its history. Looking at the properties of the cosmic microwave background, matching that up with the properties of, well, just how much stuff do we see around us in terms of ordinary matter and in terms of dark matter. And this dark energy seems to fill in a lot of those gaps very, very effectively. So even though we don't know really what dark energy specifically is, we can't test it in the lab yet, it does seem to, the models that include dark energy seem to match up with a lot of different kinds of observations very effectively. So again, this amount of dark energy explains the flat geometry of the universe and the observed acceleration of the expansion of the universe. If our universe is dark energy dominated, it seems like not only will our universe expand forever, but that the expansion of the universe will continue to accelerate and things will keep on moving further and further apart at faster and faster rates, basically forever. There is a lot of open questions on what will happen in the far, far future of the universe. Like, will the universe eventually accelerate so fast that galaxies get ripped apart and stars get ripped apart and eventually down to atoms being ripped apart? Or will eventually just the universe be expanding so much that we are the only galaxy that will be able to detect? Other galaxies are moving away so fast that we can't detect their light. I think there are still a lot of open questions, and we don't necessarily want to make a specific prediction about that until we have a little bit more data on what the far future history of our universe is going to look like. So again, just summarizing some of the key ideas about this dark energy, we said based on these white dwarf supernovas, we've identified that the acceleration of the universe, the expansion of the universe, is actually accelerating. Based on properties of the cosmic microwave background, the universe seems to have a nice flat geometry, but we don't have enough ordinary matter and dark matter to get us to that flat geometry. And dark energy, whatever it is, could make up that missing energy to give us that nice flat geometry. So again, dark energy explains the acceleration of the universe and makes up the rest of the mass energy density. Again, maybe explains isn't the best term, but there seems to be something going on, some exotic type of energy that seems to be driving the acceleration of the universe. And it seems that the universe will expand forever. At some point in the future, hopefully scientists will be able to measure something about this dark energy in the lab or in other kinds of observations. But at this point, we really don't know a lot about the specifics of dark energy. We can only identify its effects on the universe around us. So this is a huge open question in modern astronomy, and it will take new kinds of tools, new kinds of observation techniques, new hypotheses and theories about different aspects of, potentially particle physics, other kinds of physics, in order to try to answer some of these questions.